What does a scaling look like? We saw that the growth rate is 1 million per minute. So we have to scale up in advance. I cannot have like my concurrency at 10 million and then start scaling up. So I'm Gaurav. I'm cloud architect at Hotstar. I manage the infrastructure, security, monitoring. And quick show of hands, how many of you were actually watching India-New Zealand game on Hotstar? Wow. Thank you. So this graph is the actual concurrency pattern, the traffic pattern, and the people who are watching, you are part of this graph. So what we can see here is, this is the toss. This is the entire cricket journey. So you'll be able to relate to what it is. This is the toss. This was like a 3 p.m. match since it was happening in UK, and the toss used to happen around 2:30. So the first spike you see, the small one, is toss, and usually like 3-4 million people come at that time, and then there is a half an hour break and the match used to start at 3. The first spike over here you are saying is the start of the game. That particular match, it was spread across 2 days because it was rain affected. That is why you see day 1 and day 2. Look at how quickly the traffic is growing, and the other key thing to notice here is, it is not like one of the event wherein you are about 10 million, but if you look at this graph, most of the time it is about 10 million. So that shows you how resilient the platform is, how stable the infrastructure is. And the dips that you see here, these are, if you are a IPL follower, these are strategic timeout, and this is a one-day international, so these are drinks break that often happen at the 16th over and the 32nd over. And this is the graph of New Zealand batting, and they were able to go up to 13.9 million during their inning. Then what happened is, unfortunately it started raining, and then there is a sudden dip. This is the most interesting part of that day, and this is like one of the events we have never seen before. When the rain started happening, there was a dip from 13.9 to 5 million. There was nothing on the screen, right? It was just raining. They were showing some highlights. There was no cricket being played. Still 5 million people were glued to their screen, waiting for rain to stop and the match to begin. And this happened not for 2 or 5 minutes. This happened for 3-4 hours. So this event was around 6:30 in the evening, and the match was called off around 10. So for 3-4 hours, like 4-5 million people stuck on their screen waiting for match to start. And this is like first time we have seen in Hotstar, like people were like so eager to watch that match and India to win. On day 2, what happened is, New Zealand still had like 3-4 overs left. So the first spike that you see over here is when they came to bat the remaining 4 overs. Then they quickly went inside, India padded up and came to start their inning. This is the most critical part for us. The sudden spike that you are seeing, platform was around maybe 1.52 million. It went almost close to 15 million. And then there is a sudden drop. This is very, you can say, harmful for backend services because of the spiky nature of the traffic. All your services needs to like be scaled up well in advance. You cannot rely on autoscaling because it's slow in nature. And this entire scale up is almost like 1 million per minute. So that's the growth rate. Yeah, that's the growth rate that we are looking at. And then there were regular, like this is India batting, and then there were regular fall off wickets. So the traffic didn't grow that much, but suddenly then Dhoni came on to bat and he was playing really well, and all of us were thinking, okay, now we'll win the match. That's when marketing team and everyone like started sending push notifications to bring on more users, and the spike that you see here is almost like 1.1 million users being added to the platform per minute. So within a span of 10 minutes, we almost went from 13 million to 25 million. So that is the scale that we are talking about. And unfortunately, at this point, Dhoni got out. And so 2 interesting things, not interesting I'll say, but that is the time when Hotstar made a global record. But At the same time, your country is losing, so you cannot really go out and celebrate that you have made a world record. So we have to manage those mixed feelings as well. The drop from 25 to here is what kills most of the platform. If you are an Android or iOS developer, you can quickly relate to this. What happens is when you are watching a video, you are just requesting a playback file. You're just watching the cricket match. You're not doing much. There will be a bunch of API calls, but not that much. Suddenly, when you shift from video to homepage, now you're making homepage calls like your masthead, your continue watching tray. Then there is personalized content. What you have like watched previously, based on that, it will recommend you new content. So all these are API calls. What happens is when the match is being played, those API calls are not made because you are just requesting the video playback file and few APIs related to heartbeat, concurrency, stuff like that. So suddenly all 25 million users, if they exit the app by clicking home button, then it is okay. If they click a back button, all this 25 million users are going to come to home page. And at that moment, your home page need to handle that load. Yeah. And that's something that you have to like prepare in advance because you don't have time. You don't know when the traffic will drop, what will the peak will be. So there is a sudden hit and the beating that your backend infrastructure and the applications take. These slides need no introduction, but I'll just go over this point. So the day India-New Zealand match was being played, in a single day we had 100 million unique users, which is the first of a kind in the world, and it has increased our concurrency record 2.5x. So before this, last year IPL we were at 10.3, then this year IPL we went to 18.6. So from previous year to this year, our concurrency has grown up like 2.5x. And let's talk about scale, the 25.3 million number. And if you're watching the match on Hotstar that day, you must have seen this number, or like you will be part of this record. This is the peak concurrency that we spoke about, around 1 million requests per second. This is again an interesting number, 10 terabytes of video bandwidth being consumed every second. This, if I have to relate to India's bandwidth, this is almost 70-75% of total internet bandwidth available in India. And we were consuming upward of 10 terabytes every second. These are all clickstream messages, your social chat, the metrics that your app sends to the backend. Those were around like 10 billion messages. And usually we do around 100 hours of live transcoding every day. So this is the scale that we are talking about. And people may ask why 25.3 million is a big number. So to give a perspective, before we hit 10.3, the global concurrency record was with YouTube. There was a space jump event by Red Bull in Australia, which was live streamed on YouTube. The peak concurrency at that time was 8 million. And that happened in 2012. From 2012 to 2018, there were many significant events like Royal Wedding, Super Bowl happens every year, which is the biggest sporting event in United States. Then there was Donald Trump inauguration, which peaked around 4.1, 4.7 million. But in this all like 6-7 years, no one could break a YouTube record until IPL happened. At that time, we were at 10.3. This year, we went to 18.6 and World Cup 25.3. So if you look at the closest competitor, we are 3x of them. And how do we prepare? Like, it is not like one of the event or like autoscaling can save you wherein you can handle 25 million or more users, but a lot of efforts goes in the background to prepare the platform for such events. So we do a lot of game days, and what happens is there is a very large scale load testing that goes into preparing the platform. These are network tests, these are application tests, how much each application can handle. And we have an in-house project called Project Cult. And this is the amount of infrastructure that goes behind that load testing. So these are all C5 9x large machine, If you are aware, each C5 9x large machine has 36 CPUs and 72 GB of RAM. You multiply that by 3000, you will get this number. So we use 3000 or more C5 9x large machines to just generate the load. And this load generator then hits our API services or applications that we saw on the first graph, because you have to prepare the platform for those spikes. And this is the network out that is generated due to that load gen machine. So funny part was, whenever we used to do load testing, other customers used to get impacted, because in a public cloud environment, you share the network with all the customers. So, or the CDN partners, regions, or like the edge location used to get overwhelmed. So to avoid those things and others customers being like impacted, what we did was we moved to geo distributed load generation. So now instead of a single region, we have our load generation machines in 8 different AWS regions, and all of it generates the load together, so that not a single edge location or a region is overwhelmed when we perform our load testings. Beauty of this project is, apart from load generation, it helps us do performance and Tsunami testing. Tsunami is the graph that we saw in the first slide. The sudden surge and the dip, it can kill any application unless you are like prepared for. And it also helps us do a lot of chaos engineering. I'll talk about that a bit more later on. And this project also helps us to generate traffic pattern using ML. So with all the information that is available to us, we know at what concurrency how much traffic each application was handling. Basis that, we go back to drawing board and figure out what is the breaking point of each system. So this helps us deciding traffic pattern. What will happen if India bat first? What will happen if two favorite teams are against each other? So you get all those answers by analyzing this raw data. This is what the load generation infra looks like. Very simple, nothing fancy. C5 9x large machines distributed in 8 regions, goes through internet to CDN, load balancer, ALB or ELB. Other important thing is, ELB, like the name says, elastic load balancer, but not really elastic in nature. What happens is, each load balancer has its limit to peak what it can handle. These load tests, the individual capacity of one load balancer is not enough. So we actually have to shard load balancers. For each single application, we use 4 or 5 load balancers and then control them using a weighted routing, so that the load is distributed and we are able to scale our application. And common ASG application either hosted on EC2 or Kubernetes. So what does a scaling look like? We saw that the growth rate is 1 million per minute. So we have to scale up in advance. I cannot have like my concurrency at 10 million and then start scaling up, because what will happen is, by the time your EC2 is provisioned, it boots up, then your application becomes healthy, register itself under a load balancer, 5 to 6 minutes are wasted. And in a live match, you cannot afford that, because by that time, your traffic can, in 5-6 minutes, your traffic can increase by 5 or 6 million. And the ladder that you are scaling for might not be sufficient there. So you have to scale up proactively in advance. We keep some buffer while scaling up. The application boot time is around a minute, and 90 seconds is the reaction time that we have in hand to make a scaling decision, whether to scale up now or to wait. If there is a strategic timeout which is scheduled, we know that traffic is going to drop. So we have some breathing room there. Also, push notification is something that marketing team sends out, especially if there are interesting moments happening in the match, like Dhoni is hitting 3 sixes or someone takes a hat trick. What happens is, these push notification goes out to a user base of 150 to 200 million users. Even if you talk about 2 to 4% conversation, we are talking about 4 to 6 million users getting added to a platform in a very short span of time. So, and these push notifications can go out at any time, because there can be an interesting moment anytime during the game. So we have to account the buffer that we have, that push notification can go out and it should handle that spike as well. And we use fully baked AMIs. There was an interesting BOF session going on earlier during the day on infrastructure as a code, where we were discussing this as well. So we use fully baked AMIs. We don't use any configuration tools, because tools like Chef, Puppet, anything which provisions or does any configuration after the server is up adds delay to your application becoming healthy. So to save time, we use fully baked AMIs. Even the container images have whatever it is required to run the systems within itself, so that it don't have to wait for any Ansible script or Chef or Puppet to configure the application or make it self-healthy. These are few of the reasons why we don't use autoscaling, the traditional one that is available with AWS. We get a lot of insufficient capacity error. Anyone who has tried to launch a server and has faced an error that says that okay, capacity is not available in a particular AZ. Okay, so what happens is, when you want to go from 10 million to 15 million, you have to request a lot of servers from AWS. Let's say you are operating at 400, you now want 600 servers, so you are adding 200 servers. But what if you only get 50 and you don't get the remaining 150? So those kind of problems are there. Single instance type per autoscaling group. This is before EC2 fleet. So a single ASG can only support one launch configuration. One launch configuration can only have one instance type. So if C4 4x is not available and gives error, I cannot scale my application. So this is a limitation. If there is a different instance type that has more capacity, I can scale up using that. But since autoscaling group only supports one single instance type, I am blocked by that. Next is step size during autoscaling. This is again an interesting problem that only happens at scale. What happens is, when you request or you increase your target or desired capacity in an ASG, it adds server in a step size of 10, 20, that way. So let's say if you scale up application A from 100 to 800, what it will do is it will try to add 10 or 20 servers in all availability zone. And what happens is, this process is very slow, because if you want to go from 100 to 800 and you are adding, let's say this happens every 10 seconds or 30 seconds, to provision 800 servers, it's gonna take around 10-15 minutes, which is simply not acceptable when you are running a live game. And there are a lot of API throttling when activities like this happen, because you can ask AWS to increase your service limit and allow you to scale or increase the step size to maybe 100 or 200. But what now you are doing is, you are doing more damage to the system. If 200 servers launch at one go, you are making 200 control plane API calls, and these are multiple calls, like run EC2 instance API call, then there will be attach those EC2 instance to a load balancer. There will be some monitoring calls that will go to CloudWatch, because now your system is healthy, it will start reporting CPU and network metrics. Then there are disk attachment API calls, which all happens in background, but it all uses your control plane and data plane API, which is transparent to user. But at this scale, all those are fixed limit which cannot grow. So you have to operate within those things. And game of availability zone. So at Hotstar, everyone is fan of Game of Thrones. So this is a reference to that. This again is an interesting problem. So I'll give you an example. You have 3 availability zones, 1A, 1B and 1C. What happens is, if 1C has less capacity and you try to increase the target capacity of your autoscaling group, AWS, basis the internal algorithm it has, will try launching server in all 3 AZs equally. So it will launch 10, 10, 10, which will be successful. Let's say the 1C AZ only has 10 servers left, which we got now. In the second attempt, like the second cycle, it will launch 10 in 1A, 1B, but in 1C it won't be able to launch 10, because that particular AZ is now out of capacity. what happens is provisioning a server in a particular AZ is not something in our control, because that is taken care by the internal algorithm that a ASG has. In this case, it will still try to launch servers every time in 1C. What happens is when you face an error, the application adds exponential backoff. So first it will try every 10 seconds. If it fails, the duration increases to 30 seconds, then 1 minute, then 5 minutes, 10 minutes. It goes on increasing. How this harms our scaling is that one, your infrastructure becomes skewed. You have more capacity in 1A, 1B, your 1C only has 10 servers. If something happens to 1B, that AZ goes down or there is some fault, now all your traffic is being served through 1A, which doesn't have enough capacity to handle all the load, because ideally it should be like divided in 3 AZs, but now all the load has come on 1A. The second big problem is, even if C doesn't have capacity, the autoscaling group is still trying to launch servers there, which is increasing my scaling time. So if I have to go from 100 to 800, instead of getting the servers provisioned in under 5 minutes, we have seen at times where this time increases to 25 minutes. In a live match where your traffic is rapidly increasing, you cannot wait on servers being provisioned, because end of the day you cannot, like you as a Hotstar customer, I cannot come and tell you, okay, there is no EC2, that is why I am not able to show you the match. So this is what we do. Pre-warm the infrastructure before the match, and there are buffers. Proactive automated scale up. So we don't use the automatic auto scaling that AWS provide. Instead, we have developed our own auto scaling tool. What it does is, instead of scaling on default metrics like CPU, network, it instead scales up on request rate and concurrency. So we get concurrency, like the total concurrency or the total active users on the platform, and basis that we have ladder defined that, okay, at 3 million each application will have this many servers, at 10 million each application will have this much server. So that data is already fed into the system. If whichever metrics is high, if the concurrency is high, it will scale that way. If the request count per application is high, it will scale using the request count as a metric. Because CPU, unless it impacts your customer or increases your latency, shouldn't be a metric to scale upon at this scale. Because your CPU can be high, it can be 60%, 70%, but if it is not increasing your latency, if it is not creating any problem to your users, CPU should not be a metric that you scale upon. Instead, we have benchmark how much each server or each container can serve, like the rated RPS that each container can serve, and basis that we take decisions. So if at 2 million platform concurrency, I have application A which is now doing 50k TPS. If that is enough, I'll stay at that ladder. Let's say it is doing 75k TPS. So I'll scale up before because now my RPS is more than my application can handle. So that way we take decision. It is totally based on either request rate or either based on your platform concurrency. Secondary auto scaling group. This is for the problem of single instance type. So what happens is, since ASG cannot have multiple instance type, we spin up a secondary auto scaling group. So if there is a C4 large machine, there will be a secondary ASG having M4 large machine or any other instance type. And we have, so ASG also gives you scaling notification in case it is unable to increase the capacity. We use that notification, push it to SNS, which triggers a lambda function, which automatically scales the secondary auto scaling group for that application. This way, even if a single instance type is not available, still we are able to scale up the secondary instance type of that application. Last is we use Spot Fleet. The advantage of Spot Fleet is two things. One is cost savings. The second is a single Spot Fleet can allow 50 different instance type in a single configuration. So, and this is again before like EC2 fleet came into picture, which now allows you a mixture of on demand and spot. But this is what we have been following since then, because now with spot fleet you are able to configure more than one instance type. So you can have mix match compute memory intensive family. So for example, C4 4x, C4 8x, C5 4x, C5 9x, sorry, and C5 18x. This can be your base configuration. Then you spread this across 3 availability zone. So now you have more opportunities. You are diversifying your infrastructure, and chances of getting capacity errors will be less. Even if one particular instance type is not available in one AZ, there are other instance type in AZs to fill in the capacity that you require. These are the ingredients for chaos. So people here are aware of what chaos engineering is. Okay. If I have to explain it in one line, chaos engineering is something like you find out breaking point in a system, or art of breaking things, so that you know that okay, a failure is about to happen. How can you overcome it without impacting user? It's like simple. It's like more technical, but this is the best definition. So these are the ingredients for chaos. Push notification, we already spoke about this. This is not in our control. There can be any interesting moment in the match and marketing team might decide to send a notification to 200 million people. Our infrastructure backend services need to cope with that spike. Increase in latency is another problem. Even if one application in your entire user journey is impacted, what happens is it has a cascading effect on other services. So let's say my content platform APIs have increased their latency by 50 ms. What happens is there are other services that consume this API to show content. So on your homepage you have personalization engine, you have recommendation engine, which shows what content you have watched or what content you should watch. So these APIs depend on content platform API. And if that API has increased latency, this in turn will work slowly, which in turn will load the homepage slowly or may increase the app startup time. So a single increase in latency anywhere in the systems can have cascading effect to the entire application. Network failures are another scary thing. So streaming at this scale, you depend a lot on your CDN providers. What happens is if the edge location or the pop location goes down or is overwhelmed, they have to reboot or shift traffic. Now all the traffic that was being served for a particular edge location closest to your home or ISP, all those requests will now come to origin. Think about it, you are operating at 10 million and the edge location or anything like closer to your home is down. Now your request will directly come to the midgrass layer or the origin endpoint. If it comes to origin, now even if this is like 5% of 10 million, we are talking about 500,000 users. If your application is not scaled up to handle that origin request, maybe your DB can go haywire or your application may go crazy because the backend is not provisioned to handle that sudden spike. All the applications have appetite for a linear growth wherein you gradually increase the traffic. But if you have a flood of requests, let's say 500,000 requests coming to your origin, it can actually bring down your application. Delayed scale up is another problem, and that's the reason why we don't do autoscaling, because when a live match is happening and if I need to scale up, I need those servers. If it is not available or my scaling decision or scaling script takes time to scale up the infrastructure, users may be affected or they might get a bad experience. Tsunami traffic is the first graph that we saw. The sudden surge and the sudden dip both are equally bad because now your application, you can still scale, but think about your backend servers, Elastic Cache, RDS. These are not scalable on the fly. You cannot go increase your RDS, though you can do it, but there can be a downtime associated, and it's not a thing that you can do on the fly in between a live match. Bandwidth constraints is another problem. With more users coming in, you consume a lot of video bandwidth. And the stats that we saw on the first slide, it's like more than 10 terabytes per second and almost running at 70% of India's capacity. So there is very limited room to operate in terms of adding more users. Let's say the concurrency goes up from 25 to 30, 40, 50, any number. Is there enough internet bandwidth available to serve customers? Because we can push out a video, but if you are living in an area wherein there are latency concerns, the last mile latency especially, or your ISP is now choked or throttled because maybe 1000 users are watching Hotstar on the same ISP in your local area. So those are some of the things that constrains us from bandwidth point of view. And what are we looking for? Like from all this chaos engineering exercises and game days that we do, we try to undiscover hidden patterns and issues. So the main goal of chaos engineering is not to like just bring down a system, but in fact find out what happens if your one availability goes down, or if 30% of your compute capacity is taken away, or if there is some network level issue between your EC2 and your DB, will your application still perform? So those kind of tests we perform in a control environment to figure out what are the worst case scenarios that can happen if anything goes wrong in the system. We find bottleneck and choke point. This is again related to things that cannot be scaled in time, especially data stores and backend systems, which needs to be provisioned to a peak capacity because they are not that elastic in nature. Breaking point of each system. So I spoke about rated capacity earlier. So we have developed a tool in-house which now understand how much each application can take a load. So what is the benchmark number or rated capacity for each microservice or application? What it helps us identify is at what RPS or TPS application A can go down, and then we take action to avoid going or reaching near to that number, or how we can offload some of the things by maybe introducing a caching layer in between, or maybe do some API action that is not required to be done in the moment, can be done later on, like a backfilling process, something like that. Death wave is again that sudden spike, adding 1 million, 2 million users every minute. It has its own upper ceiling, right? It cannot infinitely scale up a system. So for this World Cup, we were prepared for 50 million concurrency. Though the traffic was only at 25 million, unfortunately Dhoni got out. Otherwise, even if the concurrency would have been 35, 40, we would have been able to take that beating. But let's say for this World Cup, it might have gone above 50, which is like a bit unreal in nature. But at that point, we might have like started seeing issues, or that is a territory for which we are not prepared. And failures can happen at any level, network, servers, application. So by doing all this chaos engineering exercise, we try to find out what hidden patterns are in each of these areas, and then we try to fix them. So the rated capacity, the other good thing about that is once you know your user journey, once you know that, okay, when you open a Hotstar app, these are the X number of API calls that you will make, you can scale your backend for sufficient number of users. If you don't know what is your user journey, you won't be able to scale or make your infrastructure resilient. So knowing your user journey is very important. Once you know your user journey, you can take decisions like, okay, if application A can only handle 10 million load, maybe I'll turn off that application before it reaches 10 million to avoid an outage or stuff like that. Or maybe I'll offload the processing to CDN or introduce elastic cache, something like that. And if those things are not successful, last resort is panic mode. So what happens here is, it has a very basic principle that your key services should always be up. Degradation should be graceful. The customer or the user should not know that okay, your RDS is down. So like not we should not show an error message that okay, you cannot connect to a DB. Handle that gracefully. Work out a solution wherein you can maybe allow a user. I'll give more example on that. But panic mode essentially is when you turn off your non-critical services, thereby making room for critical ones. So when 25 million people are watching cricket, that's like almost 99.99% of the total traffic available on the like active on the platform at that time. So for 0.01%, it not really matters if they need personalized content or the other non-essential things which can be turned off, thereby making room for the critical API services which delivers your video, your ad, your concurrency numbers, your key health check metrics. P0 service must be always up. So for us, P0 is video, advertisement, subscription, payment systems. All this is very essential. Non-essential services like recommendation, personalization, this can be turned off for maybe half an hour during the key or interesting moment of the match. So you reduce that traffic and you make that bandwidth available for the P0 services. And graceful degradation is for applications, like I gave an example, application A can only handle 10 million traffic, and it doesn't make sense to scale it up more by just throwing hardware capacity or anything, unless it adds a business value. So at that time, you can cut off that system, maybe return a 200 OK response so that your client doesn't create a error message or shows the user a bad experience. The other thing is the clients are also smart enough to know an application is in panic mode by returning a custom error code. So what happens in this case is, let's say your application, payment application, DB has some issues and due to which you are not able to make or complete the financial transaction, which is a known issue at our end. So what we do is we can put the payment system into panic. Now client, if it retries, will know that okay, there is a issue at the backend and not a customer related thing. It will allow you to bypass the payment and just watch the match. Same thing with the, let's say, login system. If your login system, anything like a DynamoDB in the backend or ELB has an issue or is having any error or a bug, we can put the entire login system into panic. What this does is it allows the user to watch a video without even asking it for a login or a valid subscription, because we know that okay, there is an issue at our end, so we allow users to bypass those services for a particular time till that issue is fixed. Once it is fixed, we disable the panic mode so that the normal system flow can continue. And yeah, at every ladder, like after 10 million, there are decisions taken to understand one, either this service or application is necessary for business, two, whether it is near its rated capacity. So the tool that we have created shows us in real time at what level of the rated capacity we are operating at. So if we are around 80 or 90% of it, we manually put that in panic and degrade them gracefully, so that it doesn't have any cascading effect on other systems that rely on it, because now it will return a 200 OK. So the other application will think that okay, the system is fine, and the clients will not show an error message or a pop-up which impacts your user experience. So the key takeaways are: prepare for failure. I cannot emphasize how important this is, because at this scale, especially if you are operating in a public cloud, failures are bound to happen, which are usually not in your control. There will always be a factors wherein you cannot do anything, but it's your job to overcome those and design your application or system in such a way that it can handle those failures. So that is why chaos engineering is also important. And understand your user journey. unless you understand what happens, what API calls happen in your system when a user opens the app, you won't be able to make your infra stable or resilient. You have to understand each API call. So when you tap on a home page, what all action happen in the background, which database it touches, like which API call goes from where to where. You need to know that. When you click a play button, what all APIs are called. If you know that journey, you can script that, and then you can also create your load testing pattern. And it is okay to degrade gracefully. We should avoid like showing errors to users, which impacts the user experience or adds a bad name to your brand. So whenever possible, degrade gracefully without user knowing that okay, your system or infrastructure has issues. Cool. That's all I had for today. Yeah.
So when the match was going on, were you watching the match or this?
I had to watch the match next day because in the match, like happens, sometimes we don't even get chance to look at what is happening. We look at match from a different angle. So people enjoy the match. We just look at scorecard and who is playing, so that we can take decision whether okay, Dhoni is going to come to bat. So there can be an increase of 2 or 3 million. So we have to think from that lens that okay, now be ready to scale up because favorite batsman is coming in. Same thing happens in IPL as well. Like the top 3 teams, like at least in the fan base, are CSK, MI and RCB. Whenever these teams are playing, our traffic is crazy. And there are so many Dhoni and Kohli fans. Whenever they get out, our traffic drops by 2 million, 3 million. So we look at from that angle. Sometimes like people ask me whether you saw that fantastic catch or you saw him hitting 50. We in that tense moment we don't even remember like such event that happened.
But generally, so it is taking multiple iterations to get to this level of.
Yes.
What duration? Can you give us some insight on that?
Almost 2 years.
2 years of
Yeah.
focus.
Because there are always learnings. Like first attempt you cannot always succeed, and to scale a systems, and there are things that. So for many of the problems, we didn't had any references that okay, someone has done this in the world, we can copy paste that idea. Some of the problems we encountered was very unique in nature due to the fact that no one has crossed this scale. Even with CDN partners, no one is streaming at this scale. So it adds its own unique challenges, and there are failures as well, but you learn from them and you try to do better next time. So I'll say it has taken almost 2 years worth of effort to reach this thing. And now even IPL is like far away, but our preparations have already started.
I have a small doubt here. So, here, see, you talked about the game day, right? So, how were you able to mock such a huge load onto your systems during the game day that you are doing?
So, like I said, it uses more than 3000 C5 9x large machine. These machines are scripted to generate equivalent load that 50 million concurrency users will add to the platform. And the logs and the access pattern give us values like if I say at 5 million concurrency, not all application will handle 5 million. Payments will have lower, video APIs must be having higher. If everyone is watching match, my personalization will not have that much hits. So at every ladder, each application has its own, you can say RPM, RPS at which it operates. If you find that ratio, you can script your load testing to mimic the entire graph that we saw in the first slide.
Did you actually automate the chaos testing that you have done?
Sorry?
The chaos testing that you have done, the chaos engineering.
Yeah. It's fully scripted.
Yeah. So can you tell me are there any frameworks for this automation?
Mostly it's Python based. So it depends on. So chaos engineering in our case is very. You can say there are tools available in market which does this for you, open source tool. But what we try to achieve from chaos is two things: errors that have happened in the past. If they happen again, what will be the impact? So that is why we simulate network failures, we simulate DB not being available, just to see how will it impact at 10 million versus 25 million. This is one thing, and sometimes we just randomly go and do stuff that is not even like thought of. So maybe you just if a system is like talking to another system through VPC peering, you delete that network connectivity, or you go and change your route table settings. So just see that whether the application can handle either load or performance impact if a network connectivity is not available. Sorry? It's a homegrown Python script, not using any third party tool. So these are like just Python Boto script. You just script what you want to perform. You want to change a route table, which is easily doable through a Python Boto. No, no, no. The QE team does it in-house. Not yet, not yet. But it's very simple. Like removing a route table entry through Python Boto is just like 3 or 4 lines of script.
About the panic mode that you talked about, like bypassing any other service like payments or something. So is it like just a feature toggle that you have implemented for
kind of feature toggling at client level, and at the backend level custom error codes which return a OK response instead of a 4xx or 5xx.